Now we're going to look at applying Gauss's law in general and understand what it is Gauss's law allows us to do and specifically what it doesn't allow us to do. So what applies, what doesn't apply? Well, Gauss's law, as it shows here highlighted for us, is given by this boxed equation. So the flux through a closed surface, that's the integral with the circle, is given by the electric field coming from the enclosed charges, and I'll get more into that in a moment, dotted with n hat dA for our surface. Our surface in the example I have shown off to the right here is my red dashed Gaussian surface. You can think of it like an eggshell, so even though it is drawn two-dimensionally in the page, think of it as a three-dimensional type of eggshell enclosing positive Q1 and negative Q2. And please make sure you get this into your notes. This is really important. The Q enclosed is always the net Q enclosed. So the Q enclosed you're going to use in your equations will always be plus or minus Q enclosed 1, plus or minus Q enclosed 2. And if there are more, we can simply add and subtract. Now the external Q's, as it says here, have no effect on the flux integral. So let's just quickly make sure we understand why that is the case. And now that we understand solid angle, we definitely can understand why that is the case. If we consider the solid angle coming from an exterior Q, then that exterior Q makes a solid angle in here, a small one, and a bigger solid angle out here. And we saw that our dot product shows us that we can always get the projection onto a perfect circle, a perfect sphere. And since the electric field, according to Coulomb's law, right, is proportional to 1 on r squared, the solid angle, we know, is proportional to r squared, right? So the area, I should say the area, the delta A, is equal to r squared times the solid angle. Those r squareds cancel out, and the flux calculation, the flux in this case, right, because it goes opposite to the n hat vector, and the flux out, positive, because it goes in the direction of the n hat vector, will cancel out perfectly. So always, 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 external Q's do not contribute to the flux integral. So what we can do with Gauss's law, we can always use Gauss's law to calculate the electric flux through a Gaussian surface due to the enclosed charge. So that we can always do. We are going to see that we can sometimes use Gauss's law to actually calculate the electric field, and this will only be when we go back to having the symmetry that we talked about earlier. So if the electric field is indeed constant on our Gaussian surface, then we can use Gauss's law to calculate the electric field. So we'll talk more about that in detail on our next page of notes. Gauss's law in general does not give us the ability to calculate the electric field. We must have symmetry to be able to do that. In other words, our dashed red Gaussian surface here has to be spherical around a point charge, or cylindrical, we'll see, around a line charge. So I added one little bit to the notes here, an example question, because I found students have struggled a little bit with this concept at this point. So let's go through this together. And we're going to consider Gauss's law and talk about which of the following is true. So based on Gauss's law only, based on this equality only, is it true that the electric field in this equation is due to the enclosed charge only? Well, the electric field on the surface of the Gaussian surface is not only due to the enclosed charge. So the electric field in general at this point in space will be due to all three. So in that case, Gauss's law doesn't tell us that the electric field at the surface has to be only due to the enclosed charges. If Q enclosed equals 0, so now we're at B, so if Q enclosed equals 0, E equals 0 everywhere on the Gaussian surface. Well, that again is not necessarily true because you can have outside charges putting electric field on the Gaussian surface as well. C, if the charge inside consists of an electric dipole, then the integral is 0. That is definitely true because the integral itself only addresses the Q enclosed. So this is true, yes. E is parallel to the differential area along the surface. That is not necessarily true. E does not have to be parallel to dA along the surface because the electric field can point wherever it wants, right? So my electric field here, right, does not point parallel to dA along the surface necessarily. If a charge is placed outside the surface, then it cannot affect E on the surface, and this is exactly what we've been talking about. Electric field outside does affect E on the surface. So I have it more completely written down here in terms of our answers. So please make sure you get this down into your notes, and we will definitely be talking more about these concepts as we go through some example problems on our coming pages of notes.